So comets are these things, right? They're very pretty. Kind of, actually, let's just open this in a new tab. Gas tail, dust tail. Ooh, see? People have already, yeah. So comets are really cool. They are very similar to asteroids in a lot of ways, okay? But there are some differences. Does anyone know the differences, the main differences between comets and asteroids? So remember last time we talked about asteroids versus meteors versus meteorites, right? Repeat?
Comets are icier orbit.
Couldn't have said it better myself, man. So comets are icy and they orbit the sun in very elliptical orbits. Couldn't have said it better myself. Comets are described by a lot of astronomers as dirty snowballs. Okay. Most of their material is actually made of water ice, and most of it is concentrated right here, okay, in what we call the coma. And comets have tails for a few reasons, okay? So as you can see in this image, this comet actually has two tails, all right? And all comets have two tails. You can't always see both of them, but they do always have them, okay? So this is what's called a dust tail, this portion right here. This is material that is coming off of the surface of the comet itself. And this is ice and rock and dust that is breaking off of the surface of the comet and being left behind. So you can kind of think of it as like as a rock or a snowball that is crumbling, okay, as it's going, and it's leaving behind a trail of stuff, all right? And the reason why it leaves that stuff behind is because the ice inside of the comet starts to sublimate. Sublimation means going from a solid to a gas. So here in the coma, we have an actual physical object, this big piece of something, all right? And we have even landed some stuff, quote unquote, landed some stuff on a comet. 67P Port Authority? No. There you go. Churyumov, Gerasimenko. But I don't want the size. So this is 67P Churyumov, Gerasimenko, which is the comet. And I know it doesn't like look like much. So this is what the inside of the coma looks like. So when we look at this right here, the thing that's actually in here, looks similar to this. All right, it isn't this one, but it is similar. Okay, it's kind of like an asteroid, but it's mostly made out of water ice. And as the comet comes closer to the sun, it starts to break apart because the water ice inside of it starts heating up, and it shoots out these geysers of gaseous water. So it starts breaking apart because it's kind of like a pop rock. Who enjoys pop rock candies? It's kind of like a pop rock. Like when you dump them in and they start popping like that. That's what's happening to the comet. Okay, the comet is starting to break apart because there's gas that is being expelled out of the surface of the comet, and it starts breaking up and sending out all of its guts behind it in what is called the debris or dust tail. Okay. and it's left behind in the orbit as it is spewed out into space, okay? So what is the deal with this second tail? Does anyone want to take just a stab at what might be happening here with this second tail? This tail is not made out of stuff. Like, it's not made out of matter. No, mostly. Repeat?
Like refraction through.
Ooh, refraction. That's an excellent hypothesis. So when I said that it's not made out of matter, that's not exactly true, but it's not like dust or debris or pieces of stuff. This is ionized gas. Okay, these are ions that are being charged by the sun. Okay, so this is called the ion tail. And the ion tail always points directly away from the sun. So the sun is over here, right, in this direction. As the comet breaks apart, it leaves behind the dust and debris in its orbit, but the gas tail or the ion tail is always pointing directly away from the sun because the sun's solar wind ionizes some of the particles and they start emitting light. Okay? Yeah.
Well, if the comet is orbiting the sun,
Mm-hmm.
wouldn't they be at 90 degrees from each other?
Not always. So this is when the comet is approaching the sun. When the comet is at its perihelion, which is a fancy word for closest point to the sun, they are perpendicular to each other. Because the comet is moving almost completely sideways relative to its trajectory in the sun. So you have all right, you forced me. I know that you don't want to see this, but I've got to do some drawing. You forced me into it, Oliver. This is all your fault, remember.
I feel like there's some interesting math.
There is very interesting math that we could do with it. That is for sure. Okay, let's do it, says Oliver. Okay.
What is the perimeter of the ellipse?
The perimeter of an ellipse?
Yes. Might be easy.
No, I don't want to. Okay, so let's change to highlighter so you can see it better. What? Highlighter, there we go. So this is the sun. In fact, I've changed my mind. Remember that the sun is primarily green. I just like to mention that fact as often as possible. So there's the sun. All right, and we got our comet. Let's do black here. The comet is the orbit of the comet. Let's do the orbit as red, and let's make it thinner. The orbit of the comet is very elliptical, so it goes like this. Woo! Okay, that is terrible, but we'll make it work. Okay. So the comet doesn't actually start breaking apart until it reaches the inner solar system, when it starts getting hot. Okay, so let's say it reaches this inner solar system there, inner solar system here, okay? As it is approaching the sun, you have the debris tail, which we will do in yellow, following behind perfectly in its orbit. And we have the ion tail, which we will do in blue, pointing away from the sun. Okay, as the comet gets closer here, it's now traveling sideways like this. The ion tail comes out this direction, or rather like that. And the debris tail is perpendicular to that. Do you see how that works? So the angle between the two is always changing as it goes around. This is always interesting when you see the two tails like 90 degrees from each other. It looks very strange, but that's just the way that it works. Okay? I know that you're all appreciative of my beautiful art skills.
Okay, so and the debris trail. Well, and the ions trail be like more than 90 degrees.
Probably. I mean, as it gets close. Oh, no, not really, because when it's moving away from the sun, then it would be like this. Actually, let's do it here. Yeah, you're right. As it's moving away, it would be the ion tail would be out here, and the debris tail would be here. So yeah, you can get it. You can get an oblate kind of a pretty funky. Okay. So here's some interesting facts for you about how these comets work. So this debris tail, the dust tail, these are actually the causes of our meteor showers. So every year you might hear about people like, oh, there's this big meteor shower coming up. The reason why we know that is because it happens year after year after year. And it happens every year at the same time of year, right? Now, I think there are 6 major meteor showers in the year. The Leonids, the Perseids, the Orionids, the Aquariids. Anyway, and these happen because the Earth is sweeping through the debris left behind by a comet that has come through the inner solar system. The biggest debris, the biggest meteor shower of the year, which is the Perseids, is actually caused by the debris left behind by Halley's comet. Okay, pretty interesting. But what is, I think, even more interesting is where these things come from. These things come from way out in the solar system. All right, most comets originate in their orbits, so like the farthest point from the sun is somewhere beyond Pluto. And they come swinging into the inner solar system and get hot enough to vaporize their water and ionize those molecules. Pretty fascinating. Okay, this is what Churyumov-Gerasimenko looks like from afar. People have called it the rubber ducky.
It does look like the rubber duck.
Kind of a double sphere. I think it's really cool as well. Let's see, Philae. So the European Space Agency sent this mission called Rosetta to go look at 67P Churyumov-Gerasimenko. And Rosetta did some like orbits around the, and when I use the term orbit, I use that very loosely. It went in a very slow circle around the comet here. And it had a little lander called Philae. And Philae was designed to go down to the surface and harpoon itself to the surface. The gravity is so low that just the spin of the comet itself is enough to like kind of nudge this little lander away from the comet. And so it was supposed to touch down and harpoon itself to the surface, hold itself down. Well, the harpoons didn't work, and it ended up bouncing and then resting up against a cliff face. And for a while, we didn't know where it was. We had lost it, but we found it in the shadow right here. Little Philae, just hiding next to on this. And there was some art and stuff that legitimately like made me cry. should probably spell that right. Philae. Yeah, little Philae here. This is the European Space Agency logo. And they had like a whole Twitter account. I got a comment. Really fun little mission. Really cool. So I thought it was so cool. And so, and then Rosetta just crashed itself into the surface before the end of the mission. Yeah, go for it. All right, so that's what comets are, and that's how they work.
Was Rosetta supposed to crash?
Yeah, yeah, it was intentional that we crashed Rosetta into the surface as an end of mission. So 67P Churyumov Gerasimenko was going back out into the outer solar system. And we don't want to just not know where our stuff goes. And so in order to make sure that it didn't like go and crash into something that it shouldn't crash into out in the solar system, I don't know, or get launched out into interstellar space.
Why would that be bad?
we want to know what happened to it. We want closure, I guess.
You couldn't have sent it off to crash into some other planet and get some good images or something?
That would have been very, very difficult. The amount of fuel needed would have been a lot to change its trajectory. Yeah, that would take even more fuel to bring it back to Earth. It would. The whole problem is you get out there and then you're kind of set on your trajectory. You can't change it unless you have fuel. So anyway, they crashed into the surface. Pretty cool. So next thing, we need to talk about the Kuiper belt. All right. Some people say the Kuiper. Yeah. So this is the Kuiper belt. The Kuiper belt is kind of a region out in the outer solar system of a lot of small bodies, dwarf planets, asteroids, comets that are way out here. Voyager 1 and 2 and Pioneer 10 and 11 have passed through the Kuiper belt. New Horizons is in the Kuiper belt. New Horizons was the one that went by Pluto. So Pluto is in the Kuiper belt. It's kind of asteroid belt 2.0. So we have a main asteroid belt in between Mars and Jupiter. And then we have the Kuiper belt, which is asteroid belt 2.0. It's just farther out in the solar system. So here's the orbit of Pluto, this yellow line with the red dot. This is Pluto's orbit here. So that's the Kuiper belt. It has probably hundreds of trillions of rocks and snowballs, all going around the sun. Camera, quickly. Okay, and they're all going around the sun.
Well, I thought Voyager 2 crashed into Jupiter.
Nope, that was Magellan or Galileo. Both of those actually crashed into Jupiter. Okay, so the Kuiper belt is going around here. Okay, bunches and bunches and bunches of stuff. This is where comets originate, most of them. So something happens where like a rock will bump into another rock, and then they just go woo, and they go into the inner solar system. And that's where comets come from. Okay, so this is the Kuiper belt. We're going to quickly move to how did it turn?
Yeah.
It did a gravity assist around Neptune. Woo!
That's description of it.
Yep. And Voyager 2 did a gravity turn around Jupiter. Woo! Well, all of these actually did gravity turns to using or what's called a gravity assist. Jupiter is really handy because it's so big that you can get a lot of velocity from it, and you can get kind of slingshotted out into the outer solar system. It's kind of cheating without using fuel. So that's the Kuiper belt. The Oort cloud, and yes, that is not a typo. It is 2 O's. 2 O's RT is a hypothetical cloud of material, mostly asteroids and comets, that is way out there, like way up. Okay, we're talking about up to a light year away. Okay, so some of this stuff that's out here, so the Kuiper belt is flat. Okay, it's flat and goes around in the same plane as the solar system. The Oort cloud is probably, according to what the math tells us, should be kind of this spherical collection of things that all go around the sun, but they're very, 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 very far away. Again, up to a complete light year. So it would take the sun's light a full year to reach the edge of the Oort cloud, which is crazy. It gets here from the sun to here on Earth in 8 minutes. If it takes that long to get out, if it takes a full year to get out to the edge of the Oort cloud, that is a really, really far distance. And that kind of gives you an idea of how strong the gravity of the sun is and how far the gravity of the sun reaches. The sun is so massive that its gravity stretches out strong enough to make these objects orbit around it even at a full light year away. Okay, we do not have any direct evidence of this collection of stuff. All of the math tells us that it's probably there, however. Okay? Questions about comets, the Kuiper belt, or the Oort cloud? Yes, repeat.
Are there comets that come from
So there are comets that come from the Oort cloud. They are hyper long period comets.
Do they go faster than others?
They do go faster when they get closer.
Well, I never know this stuff.
They go faster relative to the sun when they get closer, but they orbit the sun like every 10,000, 12,000, 18,000 years. So humanity has probably only recorded the arrival of 1 or 2 of those in our history, because we've only had recorded history for 10,000 years. Okay? All right. We are going to finish my video here, and then